My name is Kyung-Min. I also go by Jason. Today I'm here to present Outatime, which uses speculation technique to mask network latency in cloud gaming environment. This is the work that I started doing as an intern at Microsoft Research and continued on. So let's talk about mobile games here. And as two previous talks talk about it, mobile games are very popular. And people actually play very simple and basic graphic games such as Angry Bird, Fruit Ninja on their mobile devices. But wouldn't it be nice if they were able to play very high-end quality graphics games, the one that you will play on Xbox One or high-end PC games? But unfortunately, mobile devices have a limited hardware capability that limits that. And to remedy this problem, the cloud gaming platform has emerged where client merely captures user input and send that to over the network, and all the computationally expensive job happens in the server, where server performs advanced game logic, renders high quality graphics, and send back to the client, and client merely just decodes that video stream. And companies like NVIDIA and PlayStation already started, doing these services. NVIDIA, you can use NVIDIA Shield tablet to play a diverse set of NVIDIA games on that tablet. And in PlayStation Now, using PlayStation Now, you can play a library of PlayStation games on your TV and mobile devices. So here I'm going to list the benefit and drawback of cloud gaming. And notice that first thing that you will notice that the list of the benefit of cloud gaming are very similar to the traditional benefit of traditional cloud-based applications. And they are just in this similar, but in cloud gaming environment, all the benefits and drawbacks are more magnified. So let me go through a couple of them. So first of all, by running game on the cloud, you have powerful servers. You can run more advanced AI logic. You can render high quality graphics. Also, by running a game on the cloud, it limits the client dependencies, because clients just need to capture user input and able to perform decoding. So you can develop a game and make it easily client for iOS, Mac, Windows, Android, and so on. Also, it's easy to perform maintenance and upgrade, because the game itself is running on the cloud. You no longer need to push the updates to the client. And obviously the piracy is going to be different. And now people get this library of games like they are accessing Netflix, that they can just choose and play at any time at their will. Despite all these benefits, the cloud gaming also has some drawbacks. In today's talk, mainly I'm going to focus on network latency. Network latency could be very high in a mobile network, which is going to be very bad for cloud gaming environment. Also, I believe the network latency is the most important problem, because if you don't have small enough network latency, you cannot have the high interactivity that you want for playing cloud gaming. So let me go through a quick example of how cloud gaming would work in a very ideal scenario when there's no network latency here. Here I have a server and client timeline, and we have a server and a game running at 30 FPS, meaning that each game tick represented by T0 and T1 and so on are approximately 32 milliseconds apart from each other. So at T0, client receives an input I0 from the client and send that to the server. And since there's no network latency, server receives it instantaneously. And upon receiving the input, server performs some processing and then generates F1, which is the generated frame based on I0, and send back to the client. Now this client will just merely have to display this F1 at T1. Notice that both server and client is working against deadline here, that server needs to perform its processing job within this 32 millisecond window before the next user input arrives. And the client also needs to display its frame within 32 milliseconds, because the next frame is going to arrive. So although that was a nice scenario, but now let's be more realistic and add some network latency here. So here I'm adding network latency of 128 milliseconds, which is in our game tick scenario approximately 4 game ticks. So since user input gets delayed to the server, instead of getting F1 at T1, the client gets F1 at before T5, and basically all your frames are delayed by 4 frames. And when this happens, lagging starts to occur. So when lagging occurs, as you can see on the left side, you have a little guy who's trying to shoot at the guy who's soldier moving left. Since your user input is delayed so much, by the time your bullet arrives, the player's already gone. And when this happens, you feel like you're fighting against Neo in Matrix in a gaming environment, where you're constantly shooting and you can never kill the opponent. And from the studies that it's shown that players are sensitive to as little as 60 millisecond network latency. So how can we tackle this inherent problem of high network latency that could be present in a mobile environment? Our key insight is going to be that we're going to use speculation. So what we're going to do is when server receives the input from the client, it's going to do a little bit different. Now the client server is going to try to travel time. So given a user input at T2, it's going to look at what user have done and try to predict what user's most likely action going to be in the future frames. And it's going to generate a future frame based upon user's current input, which I noted as f'5 here. And it's going to send that f'5 to the client. And upon receiving this speculated frame, client is going to do two things. First, it's going to check if the server has made perfect prediction. If server has made perfect prediction, that's good. The client can display f'5 as it is. If server made some speculation, client is going to perform some state approximation at the client level to handle misprediction to show something that is closest to the ground truth state. And by using this approach, that user at the client level feel like its latest input gets updated on the display almost instantaneously, and you don't see any perceived delay if we have good prediction model and we have good way of handling mispredictions. So here is the overview of our system. Outatime client and server is going to do the work that traditional cloud gaming client and server does, but it's going to add some more work on top of to it. So here are the list of standard client and server jobs. But Outatime is going to do a couple more things. So first thing that it's going to do is at the server level, as I said before, it's going to perform speculation, and it's going to also render speculated frame. And since we're speculating, we can make, we're going to make some mistakes. So on the server level, we're going to have some way to unwind the misprediction, mainly using checkpoint and restore mechanism. And the client level, we're going to have some mechanism to handle misprediction. And to preview our result a little bit, we tested Outatime on 2 action games. And from the user studies, we can claim that Outatime can support up to 128 millisecond network latency. In today's talk, I'm going to mainly focus on two things. Using first thing is how we perform speculation and how the client handles mispredictions. As I said before, we want server to make some speculation about user inputs. But if you think about it in a gaming scenario, at any given time there are so many actions that user can take, and we need to have some sort of mechanism to be able to predict those actions. And one way of doing that is we create a taxonomy of input events. Basically, we categorize input events by these 3 categories that we did, and we perform different speculation for this type of events. So let me go through each one of them. First, for navigation event, navigation events are your basic movement event, like you're moving forward and backward, moving left and right, and looking up and right. And these are basically very continuous and smooth type of actions. And secondly, we have an impulse action that could happen at any time at user's will, such as firing a gun, casting a spell. And these events are inherently very bursty. And lastly, we have a delay tolerant event where, opening an in-game menu or switch weapons, that users don't really care about if these actions are delayed. So if you open up in-game menu, if it's delayed by 120 millisecond latency, the user doesn't really care about it because it doesn't affect your gameplay. So first, I'm going to go through how we perform speculation for navigational events. So here again, we're simulating we're running 30 FPS, and at the out-of-time server level, let's say we want to mask 250 millisecond latency. So that means we need to predict what user input is going to be for next 8 game ticks. And for instance, at T0, we received an input saying that user has moved left and looked right about 2 degrees. And what we want to do is we want to answer the question, what user is going to do for the rest of the game tick. And to answer this question, we use markup prediction model with training data based on user traces, and you can refer paper for more details on this. So how accurate is our prediction? So here we have 5 dimensions of navigation, and as you can see at 64 millisecond latency, our prediction is actually pretty good. We get about 90% accuracy on all 5 dimensions of navigation. But as you can see, as network latency increases, our accuracy decreases. So mainly one thing you should notice that the accuracy for yaw angle prediction is getting really, really worse as network latency increases. And this is because the people actually tend to look and left and right a lot in Twitch-based Doom, first-person shooter game like Doom. And again, this is very independent accuracy, and if you join these accuracies together, then you get worse accuracy. So we need to have some mechanism to handle misprediction. And that's where the image-based rendering comes in. So image-based rendering is computer vision technology, I'll refer it as IVR, that given an image and given an image's input depth, you can actually generate any arbitrary view angle and viewpoint of that image. So in this scenario, you have an input image where it's kind of hard to see in this slide, but you have 3 small dots in the very center of it. But using IVR technique, we can actually shift the viewpoint as if user has moved to the left a little bit, moved forward a little bit, and as if user is looking at the right. So you can see that outputted image has that 3 little yellow lights are on the right side. So although this IVR technique is cool and nice to use, it cannot do anything about the information that is not shown from the original source image. So since it does not know what's left of that actual input image, it's going to have this blackness on the output image, which is not ideal in our scenario, especially when our predictions are wrong. So what we want ideally was we want to have an output image that is seamless like this. And to achieve that, we're going to use cube map along with IVR. So what cube map is you take, with the field of view of 90 degrees, you take view of your horizontal view of front view, left, right, up, down, and back, and you generate a cube scene of your scenery. So you take 6 shots and you stitch those images together, and using this cube map, you can seamlessly create any arbitrary viewpoint and view angle. The problem is this approach is that we are now rendering 6 cubes, 6 images rather than just 1. And one thing that we notice is, again, people are very creatures of habits. So from the experience that we've done, that you can see that 99% error coverage for pitch angle is very low. Meaning people don't really tend to look up and down that much. And they actually spend more time looking left and right. That's why our accuracy is worse in yaw angle prediction. So noticing this, we can actually click the cube map to cover more horizontal area and cover less vertical views so that we can optimize we can make some optimizations. So now I showed you how we make speculation for navigation events and how we compensate at the client level. I'm going to switch gears and talk about impulse events. So again, we have a back timeline here at T0. The server is trying to predict what user is going to do for next 8 game ticks, which we're trying to mask about 256 millisecond latency. So again, here I'm going to focus on the fire event. So at any game tick, user can either fire or no fire. They have binary choices. So if we actually explore all the possible states, then user actually has 256 choices, and it's infeasible to just speculate all these possible branches. So to remedy this problem, we use time shifting mechanism, where the main idea is that we're gonna only allow user to fire at very specific game tick. So in this example, user is only allowed to fire at T3 and T7. And what we're gonna do is if the user fires at T1 or T2, we're going to delay that fire event until T3. And the reason we can safely do so is we actually ran a user study when we arbitrarily delayed the impulse event by 60 milliseconds. Users were unable to tell the difference. So users cannot tell if their fire event has been delayed by 60 milliseconds. So this works. But if user fires at T4 and if we delay that until T7, which is the next fire window, that's going to be too much of the latency, and user will able to see the lagging effect, which we do not want to happen. So in this scenario, and the nice thing about Outatime is, since we're running speculation, we can actually go back in time and treat as if user fire at T3, when in actuality user click firing at T4. And using this approach, we successfully narrow down the space from 256 choices to only 4 choices, and we send that to the client, and client choose the right frame according to user's input. So here I'm going to show a quick video demo of Outatime. It consists of 2 major parts, the first part consists of how delayed the bullet appears on thin client versus Outatime when they're both running at 128 millisecond network latency. And second part of the video consists of side-by-side comparison of gameplay of Outatime, various RTT and various systems. So let me talk about that. So here we conducted a user study, and then we asked them to give a mean opinion score of how quality of game is, and we compared to we made people to play both Outatime and thin client at various RTT blindly. You can notice that as soon as the network latency increased to 64 milliseconds, the MOS score for standard thin client decreases significantly in comparison to out of time. And you can see that even up to 128 millisecond network latency, out of time's MOS scores stays relatively high at about 4.5 acceptable range, excellent range, while the thin client's performance drops significantly. And one of the free comments that we got from out of time at running 128 millisecond network latency are frame rates comfortable and like the smoothness. Meanwhile, the thin client the people who play thin client complained that controls were very lagged. Furthermore, if we go down to 384 milliseconds, out of time's performance drops a little bit, but it's not as bad as the thin client. And if you look at it, the out of time's performance at 384 millisecond network latency is almost as good as thin client running at 128 millisecond network latency. So I know I'm running out of time, but I want to go quickly give more details on a couple of things that we did in our paper, and you can refer to paper for more detail. The one engineering thing is that meeting the FPS deadline was extremely hard, that 32 or 60 FPS. Because we have to perform fast speculation, we have to use fast checkpoint restore, we need to have some optimization way of capturing the depth map, rendering, and all that stuff. And we did a lot of work on it. You can refer to paper for more details. Also on the client side, we also had a lot of work making a visual experience better. Although IBR is nice, it's not perfect and it leaves some visual artifacts, and we explore some options to how to limit those visual artifacts. So in conclusion, today, I showed an architecture that uses speculation technique to mask network latency, even for Twitch interactive games. And I think this is very critical for our mobile systems community, because mobile networks usually consist of high network latency. I explained the key two techniques, which uses how we categorize events into these different categories, and able to perform speculation and misprediction compensation for each one of them. And I've shown that out of time can support up to 128 millisecond network latency through a user study. Thank you.